Today we have Eric Stevens. He's a meteorologist at the Fairbanks National Weather Service, and he's very active in education outreach programs. What else? You've lived here quite a long time with the weather and worked at the Weather Service for quite a while. And but yeah, we know him because he does a lot of programs for us and a lot of activities with students that we have. So he's great. So we're really glad to have him here. So welcome, Eric. You think so, Eric?
Hi, everybody. How are you doing? My name is Eric, and I do work at the Weather Service, and I'm happy to be here today to talk about observing the weather. We have one big take-home message that I want to across to everyone today, and that is, before anybody can make a weather forecast, the first thing you have to know is what's happening right in the weather. If you don't know what's happening right now, you can't possibly make a forecast into the future. As an example of that, let's think about right now, somebody were to call you, your phone rings, and you pick up the phone and go, hello, and they say, hey, I'm on my snow machine, and I'm riding on my snow machine. Can you tell me where I'll be in an hour? You're a forecaster, right? Give me a forecast of where I will be 1 hour from now. I'm on my snow machine. And so then you sit there and go, boy, I'd like to help this person, but without more information, I can't give them any forecast of where they will be in an hour. So you would reply to this person, you'd say, well, thank you for calling, but could you give me some more information? For example, where are you? Which direction are you riding your snow machine? How fast are you going? Things like that. And so if the person then tells you, well, you know what? I'm in Deering right now, and I'm leaving Deering, I'm going about 25 miles an hour, I'm heading to Buckland on my snow machine. Then you can go, aha, well, I know it's about 50 miles from Deering to Buckland, so in 1 hour, if he's going 25 miles an hour, you'll be about halfway there. The point of this little example here is not how long it takes to go from Deering to Buckland on a snow machine, but to illustrate that in order to tell us anything about the future, we have to know where we are now. If a basketball team, if someone asks you, is this basketball team going to win their game or not, you could give a much better answer if you knew if they were behind or ahead by 20 points. If they were behind by 20 points and there's only 1 minute left in the game, you'd probably make a forecast, no, they're going to lose. If they're ahead by 20 points, they're probably going to win. The weather is the same way. In order to make any forecast about the future of the weather, you have to know what's happening right now. If there's a storm out in the Bering Sea, nobody lives right on the Bering Sea if you're not on a boat. If there's a big storm out there, it's not affecting us right now on the land. We still need to learn about that storm right now if we're going to be able to make a forecast of where that storm is going to go in the future. So, we're going to talk about 3 things that can help us decide what the weather is doing now. We can learn about the weather now so we can make a forecast. Thing number 1 is just use your own senses. Use your eyes, your ears, your skin. We can actually tell quite a lot about the weather just by using our own senses. Looking outside, you can see if it's cloudy or not. You can even tell what kind of clouds are out there. In the summertime, we have those puffier kind of clouds. Those are the kinds that can give a thunderstorm. Or in the summer and mostly in the winter, you have the flatter, more gray clouds. And it can rain or snow from those too. But we can tell just by looking at them what kind of clouds there are, or if there's no clouds at all. You just say it's completely clear today. We can tell with our own skin that it's a cold day or it's a warm day. We can know if it's raining or not. And you know what? Other than our own human senses, machines can also tell us a lot about the weather. And some weather instruments are being installed in school systems across the Bering Strait, even in just these last couple of years. And every little bit of information, every temperature reading, every wind reading, every time someone tells us that there are thunderstorm clouds building east of the village or something like that, that helps a weather forecaster understand what's happening at the current time so that a better forecast can be made into the future. And I mentioned people can observe the weather, and also machines can observe the weather. And machines are good for some things, and machines are not so good for other things. You know, a snow machine can go way faster than any person can run, so it's good to use a snow machine for going fast. A machine can measure very precisely the temperature. A machine can tell you not only is it 18 degrees outside, it could say it's 18.1 degrees. It can be very precise, more precise than we really need. But you know, a machine
can't do everything. Only a human being can tell that there are some thunderstorm clouds as opposed to maybe flatter clouds. A machine can't tell those kinds of clouds apart. And so a human is the best kind of weather observer, especially if a human uses machines. If a human uses an instrument to measure the pressure, the air pressure is the weight of air around us. We don't really feel it very much, but there is air pressure on us all the time, and a machine can measure that. A human can read what the machine says and can understand what's going on. So down here on the surface of the earth where we all live, everyone observes the weather. We use our own senses and then machines too. But you know what? To get a really good sense of what's going on in the weather, we have to get beyond our own village, our own town. We need to get a view that takes us beyond our own little spot, because the weather is all connected around the planet, and when one thing moves in one place, other weather systems respond on other parts of the planet. So we need to have a broad understanding of what's going on. And that's why, for 50 years now, people have been launching weather satellites. And now we come to our first visual aid. Okay, I brought with me today the planet Earth. And here it is. And we live right there, up on the top. There's Alaska. And in order to see all the weather that's going on here on this planet at one time, we have launched weather satellites. These are almost like the moon that we see at night. The moon orbits around the Earth. Well, a weather satellite does the same kind of thing. In fact, you'd say a weather satellite is like a little tiny artificial moon that just hangs up there in the atmosphere and rotates around the Earth like that. If you ever see on television when there's a weather forecaster and they'll stand and behind them will be a little movie loop of clouds going by, the clouds will go by, then the loop will start over and the clouds will go by again. The loop will start over, the clouds will go by again. And the weather forecaster might say something like, oh, and we can see all these storms here in the Midwest, and then there's snow over here, and the weather forecaster has pointed these things. Well, who took those pictures of all those clouds over the entire United States? Usually they're just showing the lower 48. But sometimes they show a broad view, even for Alaska here. Well, who took that picture was a weather satellite. There's a camera on that satellite which takes pictures, and then it radios the picture down to us on Earth. It just so happens that if you put a satellite a certain distance away from the Earth, it happens to be 42,000 kilometers out there, that the satellite will go around the planet exactly at the same speed that the planet spins. So it takes 24 hours for the satellite to go around the Earth. It takes the Earth 24 hours to turn. So the satellite goes with the Earth as it turns. In effect, from the satellite's point of view, it's just hovering over one part of the Earth. And that's how you can get a series of pictures taken maybe every 15 minutes and then put into a movie loop so we can see a lot go by. You see about 18 hours of weather in just a few seconds looped over and over again. It's that camera on that satellite that's hovering over one spot that took all of those pictures. The problem with that, though, in order for that fancy little orbit to work, the satellite has to be right over the equator, which is down here. But we in Alaska, we live up here. And from that satellite's point of view, looking at Alaska when you're down over the equator is kind of like trying to read a piece of paper if you held the piece of paper about like that. You can barely see that there's words on there. You can't really make them out very well. Well, fortunately, we learned about these things. Human beings are clever, and they learn from experience, that if we put a satellite in a different orbit, maybe we could see Alaska. And so that's what they did. They made a different kind of satellite. They call it the Polar Orbiter. And we live at the pole, so that's nice. Uh-oh. Am I in trouble?
No, they're just asking you to talk a little
Okay. Someone wants me to talk louder? Thank you. That's the first time in my life I've ever heard that. All right. I'll try to... Are we good? Okay, we're golden. Okay, polar orbiting satellite. The trick with that is the satellite is a lot closer to the Earth, and it orbits, I'll have to get the Earth up here, it orbits like this. It goes around the top of the planet. Instead of around the equator, it's around the top. And so a couple of times a day, it goes right over us here in Alaska. And that's nice, because then, instead of the satellite taking a picture of Alaska and it's like reading a piece of paper like this, it flies right over us so we can see it right there like that. So there's two kinds of weather satellites. These that fly over the equator, those are called geostationary because they hover right over the equator. They hover in one spot basically, and then the polar orbiters. And we like those best in Alaska because they come right over the top of us. The nice thing about satellites is they can see, maybe we have someone in Shishmaref who reports, oh, it's cloudy in Shishmaref, and someone in Kivalina says, well, it's clear in Kivalina, but there are a lot of places in between our villages where we don't have any weather report at all. And a satellite sees everywhere. That's the nice thing about satellites. You get complete coverage of a nice broad area. But satellites aren't perfect. They have some weaknesses too. One weakness is they only see the top of the clouds. There can be many layers of clouds. If you can fly in an airplane, sometimes you'll fly into some clouds and then you'll be in the clear. And then you'll fly into more clouds as the airplane goes up. And then finally maybe you'll come out on top of the last layer of clouds. Well, the satellite can only see that last top layer of clouds, so that's one weakness. And then at night, sometimes the satellite doesn't take a very good picture because there's not much to see. In those cases, the satellite will try to take pictures with temperature using infrared pictures, like night vision goggles. And that does work to some degree, but it's not quite as good as visual light. But so satellites, like everything, have their strengths and their weaknesses. Okay, we're going to put away the planet Earth for now. Keep it right there where it's safe. Okay, lastly, or I shouldn't say lastly, nextly, you may have heard about, that was no UFO, that was a weather balloon, a harmless weather balloon. Well, there really are harmless weather balloons, and I brought one with us today. And why would you want to launch a weather balloon? Here's why. Down here at the surface of the Earth where we live, the weather is a certain way, but at that same exact moment, let's say there's no wind at all. You go outside, there's no wind. But at that exact moment, high above us, 30, 40, 50,000 feet high, higher even than maybe a jet airplane would fly, the wind could be 150 miles an hour. That could happen. The point here is that the weather is very different high above us. Down at the ground, we could have a certain kind of weather. Way up there, it would be totally different. And who cares? We don't live way up there. But the weather that we get down here on the surface of the Earth is controlled to some degree by what's happening up there. And to really find out what's happening up there, we have to launch that weather balloon. And so here we go. There's 3 parts to this balloon. The first part is the balloon part. This is huge. Here we go. Whoa. This is bigger than any birthday balloon you will ever find. It's made of this very flexible, here, I'll show you how big it is. See? It's huge. It's absolutely ridiculous. And you think it's large now. You see how stretchable this stuff is. This balloon, we fill it up with helium, and you launch it. As it goes higher and higher and higher, thousands of feet, tens of thousands of feet high, it stretches because the air pressure, as we go higher in the atmosphere, it diminishes, and the balloon just gets bigger and bigger, and this material stretches, 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 stretches. It gets as big as a house when it gets up higher and higher, and eventually it'll go so far, I wonder if I can break this. It will eventually snap. The balloon will break, but it will take an hour or 2 hours to get up high enough for that to happen. This is a very interesting material here. And, okay, so that's part 1 of 3-part balloon. So there's one part, then there's a string. And then something orange. This is a parachute, because what goes up will come down. So it's nice to have a parachute on there. Okay, part 1. Part 2, more string, and then, ta-da, here's the business end. This is the whole reason that we do this. This guy. Inside this tiny little box, and they call this a radio sonde, or often referred to as just the instrument. Inside this instrument is believe it or not, this thing hardly weighs anything, it's just a couple of ounces, is a thermometer, there is a humidity sensor, a pressure sensor, and a radio transmitter is all within this box. So we fill up this balloon, fill this guy up full of helium, let it go, up it goes. It takes the parachute with it and drags this guy along underneath, and up it goes. Oh, and I don't know if you can see this, you probably can't, but there's a little tiny antenna sticking out, and that antenna, this is the radio transmitter that it uses to send the signal back down to us on Earth. And every couple of seconds, this little guy sends information back down to us on temperature, humidity, pressure, and wind. And we get the information every couple of seconds, and for a couple of hours, we listen to this guy talk as it goes up. Well, eventually, I said, this thing goes up way high in the atmosphere, it stretches, it finally rips open, pops, and this thing comes tumbling down. That's when the parachute opens up, kind of like that. Is that noisy enough? Okay. And then this guy falls to the ground. Thanks to the parachute, if this hits you on the head, it's not going to hurt. Also, thanks to the fact that this only weighs a couple of ounces, and that the box is actually pretty good for something that hardly weighs anything, it has a very low density, we would say. And the reason they made the box like this, it's actually bigger than it needs to be, given how light it is. But they wanted it to be big and light so that if an airplane were to run into this, if a jet airplane flying across the Pacific Ocean were to hit this guy, this thing would break apart because of the low density. Its mass is spread out over this whole area. It would just shatter. The airplane windshield would not break. This thing would break. That's by design. You know, these things go up and then they come down. These balloons are launched twice a day in Barrow, in Kotzebue, in Nome, in Bethel, King Salmon, St. Paul Island. Several locations in western Alaska launch these balloons twice a day, and then they all come down. Now, a lot of balloons launched in Alaska, they can be taken by these high-altitude jet stream winds. They can be taken out over Russia. They can be taken into Canada. A lot of times the balloons are taken out over the ocean. But sometimes they will pop and fall down to us again here in Alaska. And if you find one of these, if you're out somewhere on the Snow-Go or somewhere and you find an instrument like this, you can give it back to us and we'll use it again. Now, a lot of times these balloons need to be fixed up a little bit because the trip can be kind of rough. But we will recycle these instruments and use them again. I was with the Weather Service, one of my first assignments was out in Nome, and I was launching these balloons, and we would use them again. In fact, in Nome, we used only the recycled radiosondes. They were the only ones we got. There's a facility in Kansas City where they rebuild these things, and then they sent us all the recycled ones. And that was nice, because if they work, we'll use them again. Okay, so again, the topic here we're talking about is we have to observe the weather now in order to make a forecast of the future. We talked about just looking out the window or using your own senses to know if it's cold or hot. Is it humid? Is it windy? Down at each surface location where you are. You can use a machine too. You could use a barometer to measure very precisely the pressure of the air around you. Then there were the weather satellites going around our friend the Earth. Right now, over the top of us, there are weather satellites taking pictures of Alaska. And then also, we talked about the weather balloons with the three parts, including my favorite part, the big, I mean, this stuff is amazing. Look at that. I've been trying to break this, and it just won't. But eventually it does. You can only stretch it so far, and then it'll rip. But how far that is, I have not personally been able to verify. And there are a couple of other ways you can measure the current state of the atmosphere. You might have heard of weather radar as well. In Alaska, there's not much radar compared to the lower 48 states where they're just clogged with radars down there. Here in Alaska, we do have a few radars. In Fairbanks, there's a radar. There's one in Bethel. There's one in Nome. But otherwise, in northern and western Alaska, that's about it. And so the radars, they can see a little ways out. Like a bat. You've heard about bats that fly around, and bats don't see very well. And so they chirp, and then they make the echo, their sound bounces off a cave wall, and then they know, oh, there's a wall there, I better not fly there. So they chirp, and then they listen for what comes back, and that's how they navigate. A radar is kind of like that too. A radar uses light, but it sends out a little chirp of light, and then there's a special frequency of light that bounces off of clouds. And the light will come back to the radar, and the radar will know, oh, there's a cloud over there, or a cloud over there. That's how a radar can tell what's going on. The radar coverage is limited. You can see, 100, maybe 200 miles out with the radar, and that's about it. And that's certainly nice. That's another piece of the puzzle, but again, only in Fairbanks and in Nome and in Bethel. Those are the only places around here where we have radars. If you were up at Barrow, you're out of luck. There's no radar coverage up there. But we just have gotten these new radars in the last 10 and 15 years, And before that, there wasn't anything. So we're certainly glad to have all of the equipment we can get. And then, lastly, the one other piece of weather info out there is good old miscellaneous. It's getting to be easier and easier now to observe the weather, and aircraft are putting weather sensors on their airplanes. So when a big plane flies from San Francisco over to Tokyo and they cross the whole Pacific Ocean, they can be taking measurements of the air pressure and the wind, and we can find out about that. Also, ships that cross the Pacific Ocean, they can give us weather information about where they are down at the sea level, which is good information to have as well. And what we're hoping to have in these next few years is, in so many of the villages, it's so important in Alaska that we have air taxis. And we're hoping that the local air taxi operators will, they've always been giving us what they call pilot reports, where a person will say, oh, there was a big thunderstorm over the Nulato Hills east of Unalakleet. Maybe they'll say something like that. And that's good for us to know. But we're also working on getting some automated weather observing gear that will always just report things like pressure, temperature, wind installed on the aircraft. These newer instruments are not very big, but we're still developing that kind of thing. Again, all of this is geared toward finding out what's happening right now with the weather, because that's the most important part. You can't make a forecast of the future. You can't give anybody a warning about a blizzard that might be coming their way the next day, or maybe a high ocean surf that's coming to the beach in another day or so. We won't be able to do that unless we find out what's happening right now. That's the first and most important step in doing a weather forecast. So I'm done. Thanks very much.
Well, thank you, Eric. That was
Thank you.
great. Really appreciate that. And thank you, everyone. You were really good about keeping mute on. That was great.
How much has the weather changed in the last 50 years?
Oh, this is the dreaded climate change question. You know what? I usually punt on that because in the weather business, our job is to forecast in the next couple of days, and we have a hard time getting that right. And so the issues of a forecast of the climate over the next 10 years or next 50 years, or how have we done in the last 50 years, there are people who are a lot smarter than me who deal with that. And actually, maybe could I give you some references later on?
Oh, yes.
Maybe we can
and I can email them out. Mm-hmm.
Yeah. But I could refer you to a couple people who could give you a lot more information about climate change. But I can tell you this, that for Alaska, this is a very important issue because a lot of the indicators, as far as I understand it, and again, my understanding is not as complete as what some people can talk about, but that in the high latitudes, that is to say, well, let's get our planet out again. Up here on the polar ice cap and the areas around the ice cap, and that includes Alaska here, northern Canada, and Russia, in these locations, and then also down at the bottom of the planet, that those two comparatively small areas on the planet are potentially going to have much more pronounced effects from climate change or global warming than areas down along the equator. So for us in Alaska, this is a very important thing. One thing I can say is that with regard to sea ice on the Arctic Ocean here, the sea ice, in the summertime, the ice is melting back further north in the last couple of decades than it had earlier. But then in the winter it does come back. But in the summer it's melting back more. And so there's always these give and take. You know, one thing I would like to say though, with regard to climate change, is that keep in mind that variability is a normal part of weather. Short-term variability that's normal. You have cold periods, maybe it's cold for a week, and then maybe it gets warmer for a week. Or it snows every day for 2 or 3 or 4 days, and then it doesn't snow at all for 2 weeks. This variability is normal. That's the way things work. And the issue of climate change is, on a broader timescale, is there some other signal where overall things are warming or cooling or getting stormier or less stormy, on top of the fact that there's some normal oscillation. Oscillation, there's a big word that I shouldn't toss around. But, right now in the lower 48 states, they've been having some winter weather. They had freeze that killed citrus in California. They had blizzards in the Rockies and in the Great Plains that buried cattle. And in the Great Lakes, they're having lake effect snow showers, 11, 12 feet of snow in Buffalo, New York. That's a lot of winter weather. But you know what? You can still have winter weather and you can still have global warming at the same time. Because in the broad scale of things, you add up all the cold snaps and all the warm spells, add it all up, does this lead to a couple degrees of warming over time? There is still room for climate change and a lot of variability. Those are two different things that can coexist. That doesn't really answer your question a lot, but change is important.
How many days ahead can you predict the weather?
How many days ahead can we predict the weather? Good question. You know what? It depends on the situation. Some weather patterns are really tough to predict, and we can be very wrong very quickly. Other weather patterns are more stable, and we could do a reasonably accurate forecast out several days in advance. I would say if we're really lucky and things are good, we can have some kind of skill out to about 1 week. But most of the time it's just 2 or 3 days that we do our forecasting. But it depends on the situation. We're getting into the second half of winter now, and in this time we get into the second half of February into March. All things being equal, this tends to be a quieter time for weather when we can get high pressure systems that come in and sit over the area for a week at a time. And if that kind of pattern develops, then we can be more accurate with it because those are very slow moving weather systems. But in answer to your question, how far out can we make a forecast? Anywhere from 1 to 2 days to maybe 1 week.
How many people work at the weather station with you?
Okay, how many people work here in the weather station in Fairbanks? In Fairbanks we have on duty all the time, this is 24 hours a day, and on Super Bowl Sunday and Thanksgiving and everything, there are 2 or 3 people working all the time. And so we have a forecast staff of about 20 people, and we run several shifts a day. And about half of those people work on a given day, then other people have the day off. Sometimes your weekend is on Tuesday or Wednesday. Those are your days off, and then you work through the weekend. And you might be working overnight and such. But we have about 20 people who do the forecasting to cover that. 2 or 3 people on duty all the time, 24 hours a day, 7 days a week.
How long did you work in the weather station?
Okay, how long have I been working in the weather station? Well, I started in 1993, so it's been 14 years now. Long time. And I hope I'm getting better as time goes on. I've worked in Nome and in Anchorage and in Fairbanks, and I've also worked in Michigan. I was up on Lake Superior at Marquette, Michigan. But most of my time, 12 of these 14 years, I've been here in Alaska, and I hope to stay in Alaska for the rest of my career.
What's your favorite weather?
Oh, favorite weather. Boy. You know what? I think I kind of like record-breaking weather is interesting. Just like if you see in a basketball game that Michael Jordan scored 60 points in one game or something like that, something really exciting that's never happened before. There's a kind of an awesome character to the weather when it does something we've never seen before. In fact, back in June last year, it snowed in Fairbanks on June 5th, I think. And that's only the 3rd time in 100 years that it has snowed in Fairbanks in June. And then just 2 weeks ago, we launched one of these here weather balloons went up, and it measured higher up in the atmosphere the warmest atmosphere that it has ever measured for the period of November through April in the last 60 years. Weather balloons started being launched in 1948, and we had the warmest air for the winter season ever. That was really exciting. Especially after last June, we had the coldest air ever for the summer season. So that was pretty exciting to see that. But you know what? I think one reason I came to Alaska is that winter weather really makes me excited. It's just so much fun. When I was a kid, I remember looking out the window. I grew up in North Dakota, which for the lower 48 states is pretty brutal territory. They have a lot of blizzards down there, heavy snow, it gets very cold. And I remember looking out the window during a blizzard and just thinking, how can this happen, that the visibility goes down to almost nothing because of the blowing snow. And then 2 days later, there's blue skies and it's beautiful out there. I suppose everybody wonders why that happens. And so in the weather business, it's a lot of fun when you can try to solve those puzzles as they come up. I think you will find, though, that in the National Weather Service, a lot of weather forecasters are really interested in the severe weather, and that is tornadoes and big hailstones and gusty thunderstorms. That kind of summertime severe weather, which is much less common in Alaska. We do get thunderstorms, but the kind of tornado activity that they have, say, in Oklahoma, that just doesn't happen here like it does down there. And those are some serious, as we would call them, weather weenies. You know, people who are really into that kind of weather, they tend to wind up in Oklahoma and Kansas.
A quick Skype question that came from Shishmaref.
Okay, from Shishmaref.
Yes. Can you explain how AWOS stations measure visibility and cloud cover and height?
Wow. Okay. So AWOS stations, how do they measure visibility, cloud cover, and height? And AWOS, there's an acronym for you. AWOS, Automated Weather Observation System. And what an AWOS is, I mentioned earlier that we humans, we can go outside and we use our eyes and our ears and our skin, we use our senses to know what's going on with the weather, but there are machines too that can do this. And an AWOS is an example of one of these kinds of machines. It's an automated weather observation system. And one of the questions was, how can an AWOS measure visibility? What an AWOS will do is it will say, the visibility right now is 10 miles. And how does the AWOS know that? It's not as if there's one AWOS here and then 10 miles away there's another AWOS and they see if they can see each other. What an AWOS does is it has a little laser beam that might shoot from here, this end of the table, and then there's a receiver. We'll get Earth out of the way. There might be a receiver over here on the other end of the table, and the laser beam shoots over here, and if there's fog in the way or if there's snow in the way, the laser beam will be degraded or attenuated. The laser beam will run into the snow and the fog, and so less of the laser beam will make it to the receiver over here. And the AWOS understands that if less laser energy gets to the receiver, there must be something in the way, reducing the visibility. And it's a crude approximation of the visibility being reduced down to maybe 2 miles or 1 mile or just half a mile. But it's better than nothing. Again, nothing's better than a person. A person is the best way to tell how far we can see. But an AWOS uses a little laser beam that shoots across a comparatively short distance, and it attempts to relate the degradation of this laser beam to what a human would see in terms of number of miles. AWOS does a very similar thing with regard to the ceiling height. The ceiling, well, just like in a room, the ceiling is what's above us. A cloud can be like a ceiling above us. And there's a little laser beam that the AWOS shoots up, and it hits the cloud, and then some of the laser light bounces back down. And by timing, by knowing how long it took for the laser light to go up and then come back down, the AWOS knows how high up the clouds are, or how high the ceiling is, so it can see the bottom of the clouds. There's a weakness here, though, and that AWOSs can only see cloud bottoms that are 12,000 feet or lower to the ground. So if you had a big, mean cloud, but the bottom of the cloud was at 13,000 feet, the AWOS wouldn't be able to see it. The AWOS would say it's clear. But a human would go outside and, well, what do you mean it's clear? There's all kinds of clouds out there. But they were just too high up for the AWOS to see. But you know what? It's because of aviation, the Federal Aviation Administration. They put the AWOSs out there, and they only care about clouds that are close to the ground. So if something's higher than 12,000 feet, they don't even bother with it. So I think that's why the AWOS is not meant to record ceilings below 12,000 feet.
If you were to pick one key thing about weather to observe, what would one key thing be that you would pick to observe about the weather to make a prediction?
Okay. Yeah, if we could look at one, that's a tough one to pick just one. You know why that's tough? I mentioned all of these different things. There's the satellites, the weather balloons, the AWOSs we were just talking about. They all give you one piece to the puzzle, and you need all the pieces to look at the puzzle. But if you had to pick just one thing you could know in order to make a forecast, I would say you would need to know about the jet stream. That's a river of high-speed air that's high above us. Remember when I mentioned that you could go outside and maybe there's no wind at all. You stand outside, no wind. But at that same moment, high above us, 30,000 feet above the ground, it might be 100 miles an hour of wind. That's what we need to know about, that wind at the high elevations, because that jet stream can push all of the weather systems that we care about. The jet stream pushes those systems around the globe. And if we know about the jet stream, that can tell us a lot about where things are moving. So that would be the one fundamental first building block you have to have. But I'd hate to have to make a forecast only with the jet stream, because you also need the satellite pictures. But if I had to choose one, that would be the one. That was a good question, Shishmaref. Thanks.
Here's another one from Shishmaref. How far back does our historical data go in Fairbanks, Nome, or Kotzebue, and smaller communities like the VSSD community?
Whoa, good question. How far back does the weather record, the fossil record, go? You know, I can talk about Fairbanks mostly because that's the area I'm most familiar with. In Fairbanks, we have just over 100 years of weather data, although it was in 1929 that the modern era of weather observing began, when more standardized practices were adopted, and that was the U.S. Weather Bureau came to Fairbanks. Before that, the data's a little sketchy. But in many parts of Alaska, the oldest weather records go back about 100 years. You know what, though? I'll use this opportunity to point something out. In Fairbanks, we have 100 years of data, but the data's not exactly from the same place in Fairbanks. The official site of weather observations in Fairbanks right now is Fairbanks International Airport. But 100 years ago, they didn't have the airport. It wasn't here. The official site where they have recorded the temperatures and the rainfall and the snowfall in Fairbanks has moved several times during that 100 years. For a while, it was even up here at the university. And the university in Fairbanks is up on a hill a little bit. Temperatures can be different here than down at the valley bottom. So within the temperature record of 100 years, there are some changes because things move around. Always keep that in mind whenever you look at a long record of weather data, that the thermometers have changed over 100 years, that the location may have changed too. And this can introduce a little bit of what we would call noise into the data signal. That has to be accounted for. So about 100 years is as old as it gets for what we would call official weather documentation. But people have lived in Alaska for thousands of years, and so understanding of the weather in that sense can go back much longer.
So Eric, do they worry about finding the weather balloons? Could they reuse them or reuse the instruments?
Okay, well, let's bring up our favorite prop. So here's the balloon, wind. And here's this, and here is the instrument. And as far as I know, let's say you go outside and you find one of these laying around, because it went up and then it came down and you found it there. The balloon and the parachute do not get reused. When this material rips, I think it's done. It's the instrument down here that does get reused. They'll take this instrument and they'll work on it. They'll rebuild it and send it out again to be used. If it's in good enough shape, sometimes the instrument gets really beat up. And this one is dead, so we can beat it up again. It gets too damaged to be reused. In answer to your question, it's the instrument that can be reused, but this hardware I don't think gets reused. Actually, this material here is comparatively fragile. I mentioned how tough it is, but even humans when we touch it with our skin, it can stress out the material to the point when it goes way up high, tens of thousands of feet in the air, and it's bigger than a building, a small building, that the skin on the oils on your skin can compromise the rubber. So I don't think they use that stuff again.
How do atmospheric scientists study and collect data on the ozone layer?
Oh, the ozone layer. Okay. Hey, that's a good question. The ozone layer is part of the big issue, including the ozone hole. You might have heard about that. Ozone's very important. Ozone, which is oxygen in a special state, there's a layer of ozone around the Earth that protects us from the sun's ultraviolet rays. And the ozone layer has developed some holes in it, or thin spots actually, especially over the polar regions, like the South Pole mostly. And we want to measure that. To tell you the truth though, the ozone layer is way up there. The ozone layer is in the bottom of what we call the stratosphere. It's tens of thousands of feet high. The layers of the atmosphere, as you go up in the planet, you have the troposphere, that's where we live, then there's the stratosphere, then there's the mesosphere, then there's the ionosphere, and then there's the exosphere. But in the weather business, we really simplify that down to 2 layers. There's the troposphere, where we live, and then above that, everything else is called the ignorosphere. Because we just don't, for making a weather forecast of tomorrow it will snow or it won't snow, from everything on the stratosphere above, we do not deal with that because it doesn't, as far as we understand, and we don't understand everything, but right now we don't understand how this way upper layer of the atmosphere, and we're getting out toward like space shuttle elevation, how that would affect us. The ozone layer is in the bottom of that ignorosphere. And so I'm not an expert on exactly how that is measured, but I can say that most of the research in dealing with ozone is done like down in Antarctica and at the South Pole. It's more of an issue down there. But I can't say with certainty on how it's observed exactly, if they use satellites to do that, or if they're using some special weather balloons, or a combination, maybe aircraft, to do actual sampling of the amount of ozone. I would expect that they would need to use satellites a good amount to somehow measure the ozone. Good question there, Shishmarev.
If you have more questions, you can ask at acmp@gi.alaska.edu, and those questions will be directed to Eric, and he can ask any further questions for you. He's great about that. So, thank you for joining us, and it's been great to have Eric. Thank you so much. Great lecture.
Well, thank you. Thanks for all your questions, too. Interesting stuff.
Yeah, thanks. We'll see you next time.